All right, so we're starting with section 7.2 today, looking at properties of exponential functions. Homework is page 447. What was it? 7 through 31 odd? 7 through 31 odd. All right. So the properties that we're going to be talking about with exponential functions today, basically we are going to be talking about how we translate and stretch and reflect an exponential function, the same way that we have done every other function. Cameron and Nathan give those heads up. All right. So we start with this one. And we've already talked about this general form for an exponential, where we have y equals a times b to the x. Okay? And b is the value that determines if we have exponential growth or decay. If b is bigger than 1, we have exponential growth. If b is a fraction less than 1, we have exponential decay. And now we're going to talk about what we can do. What will this, if we change the value of a in front, how will it affect the graph? Just like with every translation we've done in the year. Steeper or less steep. So it'll have a stretch factor. So that a in front is a stretch factor. Okay? And if we have a negative in front of that a, we talked about this last class, what will that do? Flip. So a negative out in front of a reflects it over the x-axis. Okay, so we have this first graph, which is 2 to the x, which is the one you see in red here. And we have our xy table right here, x and y. We're looking at x values of -2, -1, 0, 1, and 2. Plugging in, we get 1/4, 1/2, 1, 2, and 4. So we're looking at this red graph. That is the parent function. With all of our translations, we had parent functions to start. We had x squared, we had square root of x, we had absolute value of x that we shifted, stretched, translated. And so our parent function here is 2 to the x. When we put a 3 in front of it, that's the stretch factor. So it means that for each x value, the y value that we had for 2 to the x gets multiplied by 3, which means that the y value is going to be up further, making this a steeper graph. So 3 times 2 to the x is the blue graph. It grows faster. All right, so that's just showing our stretch factor. All right, so let's say we have this one. And we've got the graph of y equals -1/3 times 3 to the x. So in your notes, please make your xy table the same way we did for that first example. That's y equals 3 to the x for the parent function first. And then we're going to do y equals -1/3 times 3 to the x. Make your table, please, in your notes and sketch your graph. I want to see the 3 to the x graph and the -1/3 times 3 to the x. I'll do the same up here as best I can. And we'll do that same -2, -1, 0, 1, and 2. So my red graph is my 3 to the x. So we're looking at something like that. The red graph is our 3 to the x, and the green graph is our negative 1/3 times 3 to the x. There's a stretch factor of 1/3 that makes it less steep, and then there's a reflection over the line y equals x. Sorry, over the x-axis. So it's not the scale, but you can at least see how the reflection occurs and how the stretch factor occurs. Okay? All right. So now, tell me, translating the parent function b to the x, so I'm taking 2 to the x and I am moving it like this. Based on what we know from translations in the past, how does that one move? Right, how many? Right, 4. So I want you to be able to look at these equations and describe the transformation. So if there's a reflection, you should say so. If there's a stretch factor, you should say so. Left, right, or up or down. So if I had, let's say I had y equals negative 1/3 times 5 to the x plus 7, and then minus 8. And I want you to describe the transformation. So start from the left, and what do we get? Hope, go ahead. What's the first thing you see? With the negative? Yep, so that's a reflection over x-axis. Tommy, what does the 1/3 do? Left steep. So a vertical compression by 1/3. The x plus 7, now we long?
It moves it left 7.
Left 7. And then Zoe, the minus 8.
Something is.
So it's inside the left and right when we add or subtract.
Down 8.
There you go, down 8, thank you. All right, good. Okay, so all of our functions that we've dealt with so far have had a number like 2, 3, 5, or whatever to the x. Well, there is this other number called e, kind of a special number like pi. And this number shows up in mathematics. It's one of these naturally occurring numbers. And it comes from the graph of 1 plus 1 over x to the x. You don't need to write down this table. I just want you to know where this number comes from. And that graph has an asymptote at y equals 2.71828. And this number goes on forever, just like pi. It's an irrational number that has no repeating and no ending decimal place. It goes on forever. And your calculators have a button for e, so you should look at your calculators now. Get those out. button on our calculator. You get it by doing the second and divide button. And quite often you'll see things like y equals e to the x. Well, that's just like when you have 2 to the x. 2 to the x is exponential growth. Or 3 to the x is exponential growth. Well, this is right between them. This is 2.71828 to the x. So we need to get comfortable recognizing this letter E that will show up in exponential equations. Okay, so I'm just letting you know you will be seeing that. And it comes into play when we have certain equations. So we talked about an interest equation already. We said A of t is equal to P less Q times 1 plus or minus R to the T. So that was simple interest. It's not compounded. It's just interest that's applied once a year. Well, there's also interest that can be compounded. Compounding means they split it up over the year a certain number of times, and they apply it in pieces throughout the year. And there's an equation for what is called continuous compounding, which means they break it up almost into an infinite number of little pieces and apply those little pieces each little part of the year. And to calculate the amount you will end up with when there is continuous compounding, we use the PERT equation. So this is A of t, which you see in the table, is equal to P is still that initial amount, the principal, times E to the RT, where R is still our interest rate in decimal, and T is the number of periods. Could be years, could be days, could be whatever. Generally it's years. So if we had $5,000 invested into a bank at an interest rate of 5%, compounded continuously. The key word you have to look for to use this equation is continuously. That's when you use PERT. I want to know how much I would have after 10 years. All right, once you see that continuous compounding, you immediately know you're dealing with A of what would it be this time? It's A of T, what's the T? 10. A of 10 is equal to our principal, which is what? How much money did we have to start? 5,000. Times E. The 5% we have to put in as 0.05 times the number of years, which is 10. So, do this in your calculator right now, please. So when entering in your calculator, you can put it in either one of these two forms. Answer comes out to be what? A of 10 equals what? Answer, please. Roger? 82.3. Point. Yeah. And it's money, so we'd say 0.61. 82.43? Yeah. 0.61. And that's correct. All right, so questions on the first equation. Please make sure you only use that one when you see compounding continuously. Otherwise, if it's simple interest, you use the one that we used last class, which would be this one at the top. There is another equation that's a slight alteration on this top one for different compounding, but I'm not going to bring that up quite yet. All right, so homework we already wrote down, 7 through 31 odd, and we have at least 10 minutes to get going on it. I'll put the book up on the board. This will be checked tomorrow.